Swayam Prabha. Digital India. Educated India.
In case of solid mechanics, we moved on further to look at the components of displacement, to look at the different components of total displacement. That we did by getting an expression for displacement gradient tensor in two different ways. One, the first method was more mathematical. The second one, the expression was derived by considering the different components of displacement. Okay. So, the next few slides are recall slides which are discussed for under solid mechanics. Okay. So, this slide shows the derivation for displacement gradient tensor using the first method, which is the mathematical method. So, we considered two particles, looked at the difference in displacement and expressing the total derivative in terms of partial derivatives. We could express the relationship between dux, dy, duz in terms of dx, dy, dz, and the tensor relating these two is the displacement gradient tensor. So, this is the first method in which we arrived at the displacement gradient tensor the more mathematical way. Second, what we did was we looked at the components of total displacement. We considered normal strain only, shear strain only, rotation only, and then once again got an expression between dux, dy, duz and dx, dy, dz, and the second way was more physical, because we considered the normal strain, shear strain and then rotation. So, this equation shows the relationship between dux, dy, duz and dx, dy, dz obtained by the using the mathematical method, the first method, and these two are the equations obtained using the second method, where we considered the components of total displacement one at a time, namely normal strain, shear strain and then rotation. And here the equation is in terms of the components of the two tensors. Here they are written in terms of the displacement gradients. Now, from these two equations we could write that the displacement gradient tensor is sum of these two tensors. Okay, so, the displacement gradient tensor is the sum of two tensors. The first one was symmetric, second one was antisymmetric. The first one was called as the strain or deformation tensor, second one we called as the rotation tensor. So, what we have done is split the displacement gradient tensor into two tensors, a strain tensor and a rotation tensor. Objective was to separate the rigid body motion from the deformation. We looked at difference in displacement, so that translation is taken care. To remove the rotation part, we considered each of the components separately, namely normal strain, shear strain, rotation separately, included the normal strain and shear strain into the strain tensor, and so the other tensor just represents the rotation component. Okay. So, by doing so we have separated the rotation component from the deformation component, okay. And that is what is shown here. Displacement consists of rigid body motion and deformation. Rigid body motion consists of translation and rotation. Translation has been taken care by taking difference in displacement, and now rotation has been separated, and so we are left with only normal strain and shear strain in the deformation or strain tensor. Okay. Now, what we will do is analogously we will express the velocity gradient tensor in terms of two tensors. Here again it is done by deriving an expression for the velocity gradient tensor in two different ways, one the mathematical way, the other by splitting into components, the normal strain rate, shear strain rate and the rotation rate. For the case of fluids, we will just rederive the first method, the mathematical way alone. Second one we will just analogously express it. Okay. So, now what is it we are going to do now? We are going to derive the expression for velocity gradient tensor using the first method, which is the mathematical way. Okay. Now, what do we do for that? We consider 2 points P and Q. The P coordinates of P are x, y, z, coordinates of Q are x plus dx, y plus dy, z plus dz. So, they are two neighboring points in the fluid domain. Velocity of fluid at point P, let us denote by Vp, also equal to the velocity field at x comma y comma z. Now, velocity of fluid at point Q, we will denote it as Vq, and which is equal to the velocity field at x plus dx, y plus dy, z plus dz. Okay. So, we consider 2 points neighboring to each other, and velocity at one point is v at x, y, z, and the velocity at the neighboring point is v at x plus dx, y plus dy, z plus dz. Okay. Now, let us look at the difference in velocities. Okay. What is that difference between the velocities at two neighboring points, which we denote as dv vector. So, the velocity at x plus dx, y plus dy, z plus dz minus the velocity at x, y, z. Okay. So, to proceed further, we will write in terms of the components. Let us write it for the x direction dvx. So, this tells the vectorial difference in velocities between two neighboring points. So, let us write down the difference in the x component of velocity. So, Vx at x plus dx, y plus dy, z plus dz minus Vx at x comma y comma z. Okay. Now, let us take this Vx, which is at x plus dx, y plus dy, z plus dz, expand that in Taylor series. It is a multivariable Taylor series, because it is a function of 3 variables x, y, z. So, how do we expand? The first term is Vx at x, y, z. We are expanding about x, y, z. So, the first term is Vx at x comma y comma z, and then we have all the first order derivatives. Because it is a multivariable Taylor series, we have partial derivatives. So, dou Vx by dou x dx, dou Vx by dou y dy, and dou Vx by dou z and then dz. Okay. So, if you substitute this Taylor series expansion here, Vx cancels out, and so dvx is equal to dou Vx by dou x dx, dou Vx by dou y dy, dou Vx by dou z dz. So, only these three terms remain. Okay. So, what this tells you is dVx is the total difference in x component of velocity between the 2 points that has been expressed in terms of the partial derivatives dou Vx by dou x, dou Vx by dou y, dou Vx by dou z. Other way of looking at it is expressing a total derivative in terms of partial derivative, two ways of looking at it. Okay. Let us repeat this for the other directions. Okay. Let us write for dVx, dVy and then dVz, express them in terms of a matrix. So, left hand side we have the column vector dVx, dVy, dVz, right hand side we have dx, dy, dz, and then the matrix which relates these two vectors is the velocity gradient tensor. Okay. Why is it a tensor? First, velocity has three directions. Now, we are looking at the gradient of the velocity. This gradient can be along three directions. So, totally giving us 9 combinations of directions, and hence is a velocity gradient tensor. Okay. So, what is that we have done now is derived an expression for the velocity gradient tensor by using the first method, which is the more mathematical method. Okay. We are not going to derive the expression using the second method, we will straight away write analogously from our knowledge in solid mechanics. Okay. Okay. And that is what is shown here. Okay. So, this equation is from the previous slide, expressing velocity gradient tensor using the first method. Now, if we follow an approach similar to what we have done for solid mechanics, as we are using the second method, what is that? Considering normal strain rate separately, shear strain rate separately, rotation rate separately, then we will be able to write this equation. This also relates dVx, dVy, dVz in terms of dx, dy, dz, but splits into two tensors. Okay. And the next equation writes this equation in terms of components. For example, we have seen normal strain rate as dou Vx by dou x, and then we have seen the epsilon dot xy, remember, is half of gamma dot xy, and gamma dot xy is dou Vy by dou x plus dou Vx by dou y, and then we have a half there. Similarly, we can, all other components are written in terms of the velocity gradients. Similarly, for rotation we have seen omega dot xy is half of dou Vy by dou x minus dou Vx by dou y. Similarly, you can express all other components in terms of velocity gradients. So, now based on this equation and these equations, okay, we can write the velocity gradient tensor as sum of these two tensors, and that is what is shown in the next slide. The velocity gradient tensor, that is the left hand side, is equal to sum of two tensors okay. The first one is okay, the first one is a symmetric tensor, as we can see the off diagonal elements are same, it is a symmetric tensor, and The second tensor is antisymmetric because the off diagonal elements are of same magnitude, opposite in sign. Okay. Symmetric tensor, antisymmetric tensor. And how do we name them? In the case of solids, we call it as strain tensor because it contained information about deformation, namely normal strain and shear strain. Now, this tensor now contains information about rate of deformation, namely normal strain rate and shear strain rate. All the diagonal elements represent the normal strain rate, the off diagonal elements represent the shear strain rate by 2. So, we call this tensor as the strain rate tensor. Of course, the second tensor was called as rotation tensor for solids. Now, for the case of fluids, it is the rotation rate tensor. So, we have split the velocity gradient tensor into the strain rate tensor and the rotation rate tensor, just like we expressed the displacement gradient tensor as sum of strain tensor and rotation tensor. So, this slide is that way analogous to what we have discussed for solids. Other names are there. We have seen deformation in solids is analogous to rate of deformation in fluids. So, other name is rate of deformation tensor, and all this second tensor is also called as rate of rotation tensor. Okay. In terms of more popular terminology, strain rate tensor is more popular, and then rate of rotation tensor is more popular. Okay. We will introduce some nomenclature so that it becomes handy for us later on. The velocity gradient tensor left hand side is L, right hand side the rate of deformation tensor is capital D and rate of rotation tensor is capital W. Okay. D is for D is used so that it represents deformation. We use omega for rotation, so we are using capital W for tensor. Okay. Now, whatever follows is once again analogous to what we discussed for solid mechanics. Rigid body motion of fluid is not related to viscous stress. Okay. What does that mean? Remember, our objective was to relate the viscous stress tensor to the velocity gradient, and then to understand velocity gradient we went to solid mechanics, understood displacement gradient. We come back to fluid mechanics to and then discussed about rate of deformation, velocity gradient, etc. Okay. Now, what is that has to be related to the viscous stress? Based on the discussion on solid mechanics and now for fluids also, the rigid body motion of fluid, what is that? The entire body just translating and then the entire body rotating is not related to the viscous stress. When a fluid body just translates and then just rotates, there are no internal viscous stresses developed. Okay. So, that is not related to the viscous stress. So, this tensor is not related to the viscous stress. Rate of deformation of fluid, which includes normal and shear strain rate, that only is related to the viscous stress. So, the first tensor is what is related to the viscous stress. Whenever there is normal strain rate, shear strain rate, then we have viscous stresses. So, we have to relate the rate of deformation of fluid and viscous stress, okay, which means that strain rate tensor and not velocity gradient tensor related to the viscous stress tensor. We said we need to relate the viscous stresses to velocity, then we said velocity gradient, but now we are saying it is not the entire velocity gradient, only a part of it which is the strain rate tensor or the rate of deformation tensor. Why is that? Because velocity gradient tensor also includes the rate of rotation tensor, but we have seen that the viscous stress tensor is not related to the viscous stresses are not related to the rate of rotation. Just like we discussed for solids, Remember we said if you have a solid and that just translates, just rotates, there are no internal stresses. Okay. But if you pull a solid and then change the angle of a solid up, then internal stresses are developed. Okay. So, that is why the normal strain, shear strain was related to the stress. Similarly, here whenever there is normal, you have a fluid element, that length keeps increasing, angle between two line elements keeps changing, then viscous stresses are developed in fluids. So, the strain rate tensor, not the velocity gradient tensor, is related to the viscous stress tensor. And so, the last line, we need to relate viscous stress tensor to velocity, that is what we said. A better way of saying is to velocity gradient, a still more precise way of saying is related to the strain rate tensor. Okay. So, we need to relate the viscous stress tensor to the strain rate tensor. Okay. So, like to introduce like to discuss a terminology which I have not mentioned so far, namely fluid kinematics. If you look at fluid mechanics books, fluid kinematics is discussed among the first or second chapters. Let us look at the definition. Fluid kinematics deals with describing the motion of fluids without necessarily considering the forces that cause the motion. So, just talks about motion of fluids, does not give importance or pay attention to what causes the fluid motion, okay, or the forces which causes the fluid motion. Okay. So, what are the topics which are discussed under fluid kinematics? The Lagrangian Eulerian approaches of describing flow, the substantial derivative, visualization of flow patterns, namely streamlines, path lines and streak lines, distinction between system and control volume, Reynolds transport theorem, and then decomposition of fluid motion. Okay. What is decomposition of fluid motion? That is expressing the velocity gradient tensor in terms of the strain rate tensor and then the rotation rate tensor, okay, which means that we are decomposing the fluid motion into deformation and then rotation. Okay. The way in which we have discussed is, we have discussed all these topics under the heading fundamental concepts at the beginning of the course, just like any fluid mechanics book would do, but based on the organization of the course, we have discussed this decomposition of fluid motion just now, okay, under when we are discussing strain rate for fluids. Okay. So, but these topics and this topic put together all come under the heading of fluid kinematics or kinematics of fluid motion. Okay. So, what is fluid dynamics? Fluid kinematics, we did not focus on the forces. So, fluid dynamics deals with the analysis of specific forces necessary to produce the motion of fluid. Fluid kinematics, we dealt only with motion of fluid without considering the forces. Fluid dynamics, we pay attention to the forces which cause the motion of fluid.